Hello and welcome. Howdy. Here we are. Another day. Let me see if I can see the it's working. Hello, hello, hello. Yeah, it's working. Cool. Awesome. Yeah, I guess here we are. So I wanted to keep going from where I was the other day. Let's look into this question a little bit more. So I said this the other day. This was the question I was looking at. I wanted to not look at it for a while, and I eventually decided to just dig into it and do it. So this question is an interesting one. The solution involves an algorithm that's kind of unique, and I'll go into a little more detail about it. So let's talk about this. So 1625, lexicographically smallest string after applying operations. So I've got a string of even length consisting of digits from 0 to 9 and two integers a and b. I can apply either of the following two operations any number of times and in any order on S. Add A to all the odd indices of S. Digits post 9 are cycled back to 0. For example, 3, 4, 5, 6, and A is 5. S becomes 3, 9, 5, 1. So zero-indexed odd indices mean it's going to be 1 and 3 here. So it goes to 9 and 1, right, when you add the 5. Rotate S to the right by B positions. For example, if S is 3, 4, 5, 6, and B is 1, this rotation becomes 6, 3, 4, 5. Return the lexicographically small string you can obtain by applying the above operations any number of times on S. And then it explains what lexicographically smaller means. So this is a rather interesting question. And the optimal solution, in my opinion, is kind of peculiar, kind of interesting. So the first thing to consider here is that there are two things. Firstly, there are a lot of different possible ways that like a lot of different possible results you could have from applying A several times. And then the second thing is that you're dealing with rotations by rotating by B. So there's a lot of different possible rotations you can get to. So what I decided would be a good idea, is consider that if B is even, and since this is an even string, then let's assume I cannot reach the non-odd indices of the initial string. So the initial string, if B is even, I'll only ever be able to modify those elements with this operation. And so that means there's going to be the GCD of A and 10. It's 10 divided by the GCD of A and 10, which is only going to be 2, 5, or 10 possibilities for strings that could be considered before I rotate those strings. If it's odd, on the other hand, then I can modify either of these two sort of subsets rather. And then I end up with a Cartesian product. So I end up with a multiple. Which again, it's the GCD of A and it's 10 divided by the GCD of A and 10, S squared, which is going to be either, I think it's either 10 squared, 5 squared, or 2 squared. Yes. So it's either 4, 25, or 100 possibilities. And the string is not too long. The string is only 100 characters at the most. So 100 times 100 is only 10,000, which is going to be a reasonably small number of operations. Now, the tricky thing here is, how do I handle the rotating correctly? That's where it gets really complex. So the modifying and generating the strings and sort of working through them is not really that hard. as I mentioned, you just kind of, you could just get the GCD of A and 10, and then you add that to each of these sets. And then if B is odd, then you're gonna use another for loop basically to just get the each of the variants where the other set is modified. So like that's not too difficult to generate the sets that I'm going to work with. However, for each of those strings, figuring out what its optimal rotation is given B is not trivial. That's quite a bit more sophisticated. That was what I got stuck on. That's what I was, and I didn't want to work on this problem because it's actually non-trivial, and non-trivial to the point of like quite a bit of work was done on this many years ago, like over 40 years ago, interestingly. So the way to figure out the rotation is, this is some code that I was working on previously. Let me post it into the AI, see if the AI recognizes it. But this is pretty peculiar. Let's see if it can figure it out. So this is going to do, there's some theory involved. I'll try to explain what this does. Let me see if I can actually program it again for the sake of remembering exactly what it is. It's good to kind of work those neurons. Okay. Excuse me. So the way this works is there's such a thing as a Linden word. Let's see what this says. Booth's algorithm. Okay. It's not quite Booth's algorithm, but it's similar. Oh man. I don't know if that was so as far as the theory is concerned, there's such a thing as a Linden word. So a Linden word is a word that if you have a string and you were to rotate that string, the Linden word associated with that string is smaller than all of the other possible suffixes, basically meaning that you found the optimal rotation point for that string and you rotated it. And the Linden word is that final after the rotation. That's the Linden word. That's a Linden word. There's a theorem that states that every string can be decomposed into a sequence of Linden words where each Linden word is a greater suffix, or excuse me, is a greater prefix of the next Linden word. So the last Linden word is going to be this lexicographically smallest suffix for that whole string. And to see that, there's a lemma that basically if you have two Linden words next to each other and one is smaller than the other, then you can combine them into a larger Linden word. Which I'm not going to go into too much detail as to why that is the case, but that's an interesting kind of thing that can be proven using the rotation logic. So that means that then you can basically take the longest Linden word each time, and if you do it that way, then you get that sequence of decreasing or non-increasing, lexicographically non-increasing Linden words. Why is that relevant to the rotations? Well, that last Linden word of a string, that's exactly the rotation point you want. You would bring that Linden word to the front because it's the lexicographically smallest Linden word. It also can be shown that any kind of intermediary like if you were to split the string on the linden words, like that would give you the lexicographically smallest linden word, but also the definition of linden words implies that any kind of like midpoint between linden words, if you try to rotate around those points, those are automatically larger than the containing linden word, and then that linden word is already going to be larger, greater than or equal to the last suffix linden word. All that's to say that finding the lexicographically smallest suffix, because that last linden word is always a suffix, that lexicographically smallest suffix of a string is sufficient to find the correct rotation point, to find the lexicographically smallest rotation of the string. So that's what this routine does. And so because these are going to be small strings, we'll use an int, so best I start off at 1, and then there's a k. I'll explain what the k does. And basically, we just say best is less than n, and I is less than n. Excuse me, and k is less than n. Then we're going to keep repeating, and I'll explain in a minute. So we take min of best and I. We're going to say const char, we'll say a is going to be s of best plus k mod n with some modular logic. And then b is I plus k. And what's going to happen here is we're going to say, there's a few if statements here. And then finally, there's also one more thing to check. So if best is equal to I, we're going to increment I. Come back to that. So A could be less than B, A could be greater than B, and then A is equal to B. If A is equal to B, we're going to increment K. If either of these other cases happen, we're going to reset K. And in both cases, depending on which one it is, we're going to add K plus 1. And the reasoning for this is, so this gives us a linear time algorithm, gives us the best rotation point. And what's important here is that this is going to compare, we have some best suffix that we've seen so far. And we're going to look at some point I that's ahead of best somewhere. And we're going to try to compare those suffixes to each other and figure out which one's the smallest one. And that's what the k is going to do. We're going to increment while they're equal, keep incrementing k. If they're not equal, so that's what's going on there. If they're equal, we increment k. If they're not equal, then the comparison becomes, okay, which of these is smaller? For the best one, that's the one supposed to be the smallest. So we want, this could be actually this, I might need to swap these two. So yeah, I think these are swapped actually. For the best one, if what we currently have A is smaller than what we were going to update to, then we can basically toss all of the in-between potential values. Well, there's a couple things. So there's a few things to consider here. So if we're in the smaller case, so the thing that we're checking against is not better, that means I would keep best where it is, and then I would update I to the past all of the things that were just checked at k, all these k values, and start I at another spot. And I know I can discard all of those possibilities because every possible in-between check that I would do is going to fail at that same mismatch. So all those possible starting values for I could all be tossed out. So that's why you add k plus 1. Because that mismatch is going to happen for best and any comparison to anything in between as well. So immediately can be tossed. On the other hand, if I is better, So the starting point for I was better, right? Now we have a mismatch where the best point was wrong. The other, like symmetric logic, the mirrored logic works, where now the mismatch for best versus I is actually better. That mismatch is going to happen for every value between best and k plus 1, where that mismatch occurred. So you would update best all the way to that k plus 1 position. Interestingly, best doesn't get updated to I, which is kind of peculiar. Who wouldn't necessarily think that? But for some reason, this is the way it works. Let me just check if that's exactly the right. The right code. So yeah, if we're better than, if we're best is still better, then we increment I. If best is not better, then we would increment best. Yeah, a little bit peculiar. You would initially I thought that you would update best to I when I is better, but when the I case is better, but that's actually not correct. It would, you would move best all the way to that mismatch point. And in fact, move it past that mismatch point. And interestingly, best could be I. But best is always going to be greater than or equal to I. So the other kind of peculiar thing here is that this is correctly implemented, right? Implements, okay. Lambda function implements Booth's algorithm to find the starting index of the lexicographically minimal rotation of a string in linear time. The algorithm efficiently compares potential rotations without generating them explicitly. It maintains two candidate starting indices, best and I, and a match length k. Comparison, it compares characters at s, best plus k, and mismatch handling. Character is the best, in the best rotation is greater, best candidate is discarded, skips ahead. Okay. If the character, right, so this automatically starts the next best candidate at that mismatch point. I think that's why. Is that right? Basically starts at B. Well, it doesn't, so interestingly, it doesn't actually start at B. It discards everything up to that point, which is kind of peculiar. So it kind of lags behind B a little bit, which is not obvious. Okay, both cases. Best and I, if they converge, increments that terminates. Okay. Is this a correct algorithm? Further, are you sure that this is Booth? I don't think this is Booth's algorithm, by the way. I think it's a modified Duval's algorithm. It's not Booth's algorithm. It's a well-known two-pointer variant, often attributed to Shylock, or simply called the dual pointer method, for finding lexicographically minimal rotation. Yeah, I think Shylock is the one that I got. Key differences. Booth's algorithm uses modified KMP. So it's a correct algorithm. Hello, doing good. What's up, Yash? Hope your day's going well. Welcome. Howdy. I'm doing all right. How are you? How have you been? Also, I'm glad you're here. I wanted to ask you how your interviews are doing. I had asked in a YouTube comment before, but I didn't see a response, and I wasn't sure if you just didn't see that I'd asked, or if you didn't want to answer. And you don't have to answer that if you don't want to, but I just wanted to make sure that if you wanted to answer, you had the opportunity to answer, because I was curious about your interviews. I wanted to make sure you're doing okay. And you're encouraged. Correctness and complexity. Your code is a correct algorithm for finding the minimal rotation. It runs in linear time, is often preferred in competitive programming due to its simplicity and constant space usage. Boost algorithm also correct in linear time, but generally more complex due to the failure function logic. Okay. Got it. So it's not booths. Yeah, that's what I was gonna say. I think it's not booths. Interestingly, so what I was saying before, interestingly, the best it discards the suffix up to that point, but it doesn't necessarily jump to I. Can best ever end up past I in this code? So that was something I was wondering. I was like, I don't think, no, best can never end up strictly past I in a way that violates the algorithm's logic or causes an incorrect return. Precise behavior regarding the relative positions, the overtake scenario. It is possible best to be updated to a value greater than I. Condition: this happens if previous is greater than current and the skip is large enough. Immediate correction. The code contains a specific guard clause immediately after the update logic. Explicitly handles equality. The algorithm's invariant ensures that if best jumps past I effectively becomes the older discarded candidate. In the very next iterations, best is now the larger index. Continue line trailing. However, standard implementation of this algorithm and logic, the smaller index is always the valid candidate if they represent the same periodic string. Core invariant. One pointer always points the current best candidate for the start of the minimal rotation. The other pointer scans ahead to find a better candidate. If best jumps ahead of I, it means the segment starting at the old best was proven suboptimal. The new best is now the leading candidate. Crucially, if best becomes greater than I is now the lagging pointer. Since the loop condition always increment the losing pointer by k+1, the pointers effectively swap roles or converge. Y doesn't break. If best jumps past I, best is now the larger index, I is the smaller index. In the next comparison, we compare. If they differ, the larger index might be discarded if it's worse, or I will be incremented if best is better. The algorithm guarantees that the true minimal starting index is never skipped. Benson from being equal does not explicitly swap them. Interesting. Huh. There's a nuance. Due to a large jump, self-corrects represents a position that was skipped over by the logic, proving A's best previous segment was suboptimal. Okay. So is the correctness because I is greater than or equal to best all times, or is the correctness because I and best will swap roles from time to time, and the algorithm is symmetric with respect to I and best, which is, so this is like worth asking about or wondering, questioning, like, is it, why exactly does this work, I suppose. What's up, you guys? Welcome. Howdy. Hey, do you remember me? I kind of do. Yeah, I kind of do. Yeah, I do actually. Vaguely, but I do. I did respond to that, but for some reason did not appear. Oh, yeah. Actually, I looked at the YouTube comment or YouTube video, and it said 3 comments, and I was like, but there was your comment, my comment, and there should have been a third, but it just wasn't there, and I couldn't see it. 3 interviews scheduled for the next week. The one I was about to go was rescheduled. Was rescheduled. Okay. 3 interviews. That's awesome. Heck yeah. There you go. That's fantastic. I'm glad to hear that. That's really good. The interviews are good. That's like, it's it's one of those things where like you want to prepare for interviews, but like you want to actually have interviews or going on. Very important. Failing an interview will never discourage me. I will learn from it and reapply. Thanks for keeping tabs on me. Absolutely. Absolutely. Look, I can't tell you how many interviews I failed. It's hard. Interviewing is hard. They're long. There are all kinds of questions they ask you. There's all kinds of stuff that's super sneaky. You definitely want to get all kinds of like prep work you want to do, like get people who know the corporate structure, people who know like the contracts you're going to sign. It's even worth it to, I didn't do this, but you could even contact a lawyer when you have the contract in front of you to get an idea of like what impact it has on your career. Um, I learned that 2D prefix stuff. Now I know how to solve it. There you go. Hey, there you go. Awesome. Oh, I do remember you now. Yeah, you were gonna solve a problem. Which problem did you want to solve? That was a while ago. But yeah, it's a big deal. There's a lot. Lots of interviews, lots of stuff to learn, lots of questions they could ask you. But yeah, definitely keeping a good mental like state when you're going into all that stuff is super important. Correctness relies on the fact that the algorithm is symmetric with respect to I and best, and they do swap roles dynamically. It's not required that I is greater than equal to best at all times. Okay. Treats them identically. If this is better than that, then the loser jumps ahead. If that one's better than that, the loser jumps ahead. No logical preference for the smaller index. The variables simply represent A and B. Crossing over is entirely possible for best to jump past I. That's amazing. Okay. So this is a really interesting algorithm. Like it says it's correct, but it's a really peculiar one, isn't it? That's like, so this is actually, what I wrote was not right. It should not be best. It should just be I and J, because it's actually not. It's not actually keeping track of the best. These are better than each other at different points in time. But they don't. Oh wow, that's very interesting. They don't. Excuse me. They don't necessarily maintain an invariant where one is always better than the other. That's very interesting. Okay. Wow. Huh. Huh. Effectively race forward, discarding suboptimal starting positions. The invariant is not I is greater than equal to best, but rather that the true minimal starting index has not been skipped by either pointer. Final result of the loop terminates when one pointer reaches n, or k implies full periodicity. The other pointer will be at the minimal starting index, or a valid equivalent in a periodic string. Returning min works because the pointer that reached n or went further is the exhausted one, while the other is the valid candidate. If both are less than n due to periodicity, they point to equivalent minimal rotations to the smaller index of the canonical answer. Algorithm functions as a dual pointer race where both pointers scan forward, eliminating suboptimal regions. Their relative order changes dynamically. Logic holds regardless of logic. That is amazing. How in the world is this conceived? I mean, that's crazy. Think about that. Like, what? It's symmetric, so they both. That's astounding. Conception of this algorithm is a fascinating story of iterative refinement driven by the need for efficiency in the chemical structure identification and graph isomorphism. It wasn't born in a single moment, but evolved through key stages in three key stages in the late 70s and early 80s. Booth's Campia adaptation, breakthrough Shylock's constant space, Yossi Shylock, sometimes cited as 1979. For circular list equality, refined 1981 for canonization. Two-pointer technique. You don't need a full failure table. The two rotations match. You can mathematically prove that none of the intermediate starting positions between the two pointers can be the minimal rotation. Let's reduce the space complexity to constant. Generalization, Duval's Linden words. Wow. Brilliance lies in the skip logic. The human intuition is to check every position side by one. The algorithm's creators realize that a mismatch at index k isn't just a failure, it's a proof of impossibility for all intermediate indices. This allows the algorithm to teleport past huge sections of the string, guaranteeing linear time without looking at every character's potential start. Is the original two-pointer... Did the original two-pointer idea also have this symmetry in mind? That's amazing. Which question are you solving? Oh, this one. I'm sorry. Okay, I had said the other day I was going to skip this one because it's kind of involved, kind of a tough one. 1625, lexicographically smallest string after applying operations. Yes, the original two-pointer idea by Yossi Shiliok was fundamentally built on this symmetric argument. The original conception, fast equivalence checking algorithm for circular lists, later refined. It's explicitly designed to compare two circular strings or find the minimal rotation of one without normalizing them first. Symmetry is the core principle. It was a race between two pointers. Okay, it's inherently symmetric. No fixed best. Okay. Proving that a mismatch at offset k implied that no index between the two pointers could be the minimal start. Yeah. Wasn't an afterthought or property discovered later. It was the mechanism of invention. Sought to eliminate the linear space. These variable names obscure it, but the logic is symmetric dual. Amazing. That's really cool. Cool. Okay. Thank you. So I guess the bottom line is, for something like this kind of algorithm, this is probably something you kind of memorize, because deriving it was something that happened over almost like a decade. So it happened over like a decade with several people involved. But the key is that it's a symmetric race to find the lexicographically smallest suffix. And you can formalize the argument by considering Linden words, that the last suffix is going to be also the lexicographically smallest suffix is also the last Linden word in a Linden factorization of the string, which means that this is also your correct rotation point for your string. Now, there's more to this question. So I think I said before, we're going to have if, depending on A and B, if B is odd, then we're going to do one thing. Otherwise, we're going to do something else. So it's going to be, let's let the int, we'll say A, we'll call it A. It'd be the GCD of 10 and A. Oh no, actually we already have an A. I'm sorry. Let's use a different value. Let's do just amount. We'll say the amount. And actually that's going to be for both of these, the amount. And then we're going to say GCD of A and 10. And we're going to say we're going to create a vector of strings. I'm trying to think how to do this. I want to, if B is even, I'll explain in a moment what I'm going to do. I'm now I'm learning DP. Oh, very good. The 2D prefix sum question plus or minus k range. Oh yeah. We talked about it the other day. Yeah, that was a sophisticated one. That was a tough one. That was the one that had we used a rectangular prefix, a 2D prefix sum. Yeah, it was a rectangular array that we were working with, and we wanted to find out if we wanted to find out the sum given a point or a cell in the matrix, and then we wanted to get the rectangle that was plus or minus k in the vertical and horizontal directions. So we want to get that sum efficiently, and then we were able to use a 2D prefix sum to figure that out. Yeah, that's awesome. Cool. Can you do problems from Codeforces? What's up, Aniket? I can, although more recently I've been doing the LeetCode problems. I want to try to get through all the LeetCode problems first, and then I'll do the Codeforces problems. But it's a pretty big problem set in the LeetCode problem set. But Codeforces is a little bit harder than the LeetCode, so I figured I'd do the LeetCode first, and then I could do the Codeforces. But yeah, they're both pretty good. Codeforce is a little bit harder though, my understanding overall, but they're both pretty good for practice. They're both really good. So now the next question is, so my idea here was I'm going to get this amount, and what I want to do is I want to get the lexicographically smallest string. I don't know if I need. I think I could actually use like an intermediary string. I don't think I need to do a whole vector of strings. So we're gonna do std string. We're gonna make a copy. I already have the string s actually. We can modify s here. So we're just gonna modify s directly. So for each, we're gonna do I is 0, I is less than 10 divided by amount. We're going to say constant bound. This amount also could be a constant. 10 divided by amount, which is guaranteed to be divisible because amount's either going to be 1, 2, or 5, which all divides 10. So we have this amount, this bound. And we're going to take each of the indices, and so we'll do k. The odd indices, k is less than n, plus equals 2. And we're going to say s of k is going to be set equal to s of k minus 0. So it's a digit, convert it from a character to an integer. Add the amount, take that modulo 10, and then add that, and convert that back to a character. Okay. So that creates the string that I'm interested in. And then I'm going to have a best string so far. String best. Starts off with S. And then what I'm going to do is rotate the string. So find the rotation point of S. Best rotation of S. And then I want to actually perform that rotation on S. And then I think rotate it back. We'll come back to that. Rotate and rotate back. And then we say if S is less than if best is less than S, update best equal to S. Yeah, rotate and then rotate back. So to rotate, I don't remember exactly how this code works. CPP rotate given the rotation point. There's like an algorithm to do this. I don't remember what exactly I should probably do CPP. Let me do. Okay, hold on. Rotate in place. First, middle, last. Okay, that's easier. I don't want to leak information, so when I open a new tab to enter something in there, I usually have to like take a moment to like basically set some settings, that way I don't leak information, and then I go and enter things in there. But that's kind of beside the point. Anyway, so function rotate, it looks like this will work just fine. I can just use this without doing all those extra steps. Stood rotate in place. I was going to look up the documentation for the code for this function. Rearranges elements such that the element at middle becomes the new first element. Okay, so first, middle, last element at middle becomes the first. So it should be first, middle, last is going to be rotate. First, middle, last is going to be s begin is the first, s end is the last. And the middle is going to be s begin plus rotate index. Okay, basically what we're looking for. Excuse me. So that'll rotate the string, but I want to rotate it back as well. It's not necessary to rotate it back. I don't actually need to rotate it back. That's fine. Don't need to rotate it back. Because this is always going to do the odd parts, and because B is even, the rotation, it's always going to rotate, it's always going to rotate it on those even indices, meaning all the odd values that get modified, it's going to be the same modification. So it's not, there's another element to this that I forgot that's important. It's not just the best rotation here. Because these rotation points are B positions, I have to modify my rotation code as well. I forgot about that. That's important. Let me explain that part too. So it's not going to be best rotation, it's going to be best block rotation, which is a little more sophisticated. We'll come back to that. And this is going to have a block size. Block size. And that block size is going to be the GCD of is going to be the GCD of B and 10. No, B and N, excuse me, N, where N is the size of the string. I think N I already set to, yeah. We're going to use this here. We're going to set N here. So it's going to be B and N. And let me see. Block size. So what happens now is kind of sophisticated. We get the GCD of B and N. And what this is going to do is now the blocks, when I compare characters, I'm actually going to compare blocks instead of characters. And the way this works, it's going to be, I'm going to have a subroutine here. Const auto compare blocks. And this is going to take constant A, constant B, and return, come back to what this returns, but we're going to say const bool comparison, or compare. So compare blocks. Really, there's three parts of this, right? It's less than b, greater than or equal. So there should be three elements to it. We could do, this could just be a less than. Not sure if this is better to do it like this. I'm tempted. Let's do it this way. Let's do it this way. Do a switch statement. 0, 1, and 2. I don't know if this has case or it's just default. I don't remember. I'm not sure if this is much better, but I can do it this way. So we're going to compare blocks. I'll explain what's going on here in a moment. And this one we say plus plus k. Okay. Now, what's happening here is, and this actually should be incremented by the block size. Yeah, it's not comparing it's not comparing these characters anymore. It's comparing I and j. And these are the blocks. These are no longer, yeah, so these are going to be modified by the block size. So, also, I think I'm missing this here. By the way, and S, I think. The blocks will be basically amplified by the block size. So you would multiply I and j to get the beginning of the block. You multiply by the block size. To compare the blocks, so A and B are going to be the block block indices. We'd want to loop over the block size. So we would say, A is less than B, A is greater than B, or they're equal. So we're going to return 2 if they're equal. We're going to say int I is, or yeah, we'll do I is 0, I is less than, could probably this upwards. Might as well include we don't need to include that here. So I is 0, I is less than block size, increment I, and we're going to say if S of A times the block size, so we're going to say constant begin A is going to be A times block size. begin B times block size. So if begin A plus I is less than, so we can say character ch1. This is kind of a lot of stuff just to put this in here. I. So if ch1 is less than ch2, and then else if ch1 is greater than ch2. This would return 0, this would return 1. So the block is going to be smaller if ch1 is smaller than ch2, and the block's going to be larger if ch1 is greater than ch2. And if they're equal to each other all the way through, then we return 2. And that gives us the 3 different states for the blocks. I can compare the blocks in those 3 ways. And I and j is going to jump through the block sizes. Now, the reason we're using blocks is because the blocks represent, because we don't have access to every possible rotation, because B is not 1 necessarily. We need to restrict the rotations to that subset of possible rotations. In order to restrict it to that subset of possible rotations, we note that depending on what B is, you could take the GCD of B and the length of the string and realize that a certain number of operations of B will allow you to rotate to that GCD amount. So you can always get that GCD amount rotation, and then so that means you can break the rotation subset into rotations of exactly that GCD amount. And so now you can break the rotations that you're considering into the blocks of those sections, and basically pretty much get like a one-to-one function, one-to-one, yeah, a bijection. Excuse me, you can get a bijection of those blocks to effectively characters in another string, and then consider the optimal rotation of that string. So you can apply the same algorithm, you can abstract the blocks and apply the same algorithm with those blocks abstracted. Hopefully that makes sense. It's kind of sophisticated, but that's basically what's going on here, is that realizing that we're going to use a subset of these rotations, then we can actually translate those blocks that are possible to rotate on into characters to run the exact same algorithm on those characters. However, with the caveat that we're comparing block-to-block comparisons instead of direct character-to-character comparisons. Yeah, so this should, in theory, work. And then the block size, as I mentioned, is just the GCD of the string size in B. And that actually is always going to be the case. So I should be able to put that there. And so the difference between these two pieces of code, these two cases, then becomes you just need another for loop for the odd case. So here, these rotations, these are fine. So what's interesting here, though, is that whatever rotation I use in the even case, I'm only ever going to be able to modify the, oh, this also is wrong. This doesn't go here. This goes here. Yeah, I'm only ever going to be modifying the odd indexed values anyway, so I don't need to, oh, what's up? Hey. Oh, what's up, Yasser? How you doing? Howdy. Welcome. Howdy. I'm listening to you and coding my own stuff. Oh, very good. What's up, Yasser? Forgive me as I'm engrossed in working through this here. Yeah, so but there is a slightly different thing here, where in this case I do need to consider that in the odd case, when I rotate once, I can access the even indices values. Like it's a different set of values I can access now. So what I think I would do is just perform a single rotation. Rotate it first by s begin plus b. And then I would do another loop inside here. And do the same thing. Which this probably should be a subroutine, by the way. And then put these inside of that one. So this is that double for loop that I was describing. And I actually don't think it matters how I do these rotations exactly, because these are always going to affect the same subsets of values, regardless of the rotations. And this is always going to get the best block rotation, regardless of what rotations were made beforehand anyway. So I don't think I actually need to be that careful with how I rotate things here. Yeah. So basically this one, if it's the odd case, we'll do, it'll do a square of the work. It'll do an extra inner loop. And then this one will do, if it's even, it'll only do, so if it's even, it's only 10, 5, or 2 strings to look through. And if it's odd, it's 125 or 2, or 4, rather. And that's what I expect. Let me see if I can get this best string. And if all of this works out, then if all of this works out, then this is an efficient algorithm. And it's correct. Let's see. I probably have all kinds of mistakes here, though. I'm good. What about you? I saw your stream, immediately clicked on. I can't miss you, sir. Cool, man. Cool. How are your adventures coming along? I think you mentioned you were interested in programming. I don't remember exactly what you were interested in doing. You wanted to do something. Oh, I don't know. Oh, whoops. I'm using S in so many places. Right, I don't actually need to capture it if I'm gonna put it right here. Okay, that's a good point. That's a good point. It's probably better if I capture it there, but I don't need to do that there. And then the compare blocks part. I do capture it there, though. That's kind of interesting. Okay. Maybe you should be a little more. I maybe should be consistent there, but that's not a big deal. All right. Anyway, I'm gonna leave that as it is. Let's see. What are the other mistakes that I made here? I'm sure there's plenty of mistakes. All right, somewhere line 21. Missing a. Oh, I didn't close the lambda expression. Yeah, put a comma for the lambda expression. Okay. What else we got here? Okay, wrong answers. 0 milliseconds, wrong answers. 5929, so 2050. All right. Okay, that was I was expecting, but all right. Let's see some of the other ones. So I compiled and executed, so that's kind of good. 97, so 24. Okay. I wasn't expecting that. 3928. What is happening? What? All right, let's do the simple case. So B is 1, A is 5. This one should handle it correctly. Okay, so not quite right. I have a little, I'll start it soon, nearly. Oh, that's good. I have a little knowledge about Python. I was taking class with my cousin. He lives in Germany. I've learned it a bit. I've also learned a lot of things in C. Oh, very good. C is good. Oh, that's awesome. So you started with, I know it's basic. A little bit of Python, class is their cousin. That's awesome. Lives in Germany. That's very good. And learn things in C. Sweet. Have you tried using like AI programs at all to help you to learn? Um, I think I'm just reading this. Interesting. Um, cool. Yeah, you can ask it questions and it'll tell you stuff about programming. It's awesome. I know it's basic, but hey man, anywhere you start is good, quite frankly. Like programming is one of those things where you just accumulate more and more knowledge. It's awesome. You have to be kind of careful not to forget things. It is easy to forget stuff, but because there's just so many things to remember. There's so many things. Uh, okay. Okay, 9724. All right, let's print the rotated strings. So here, so B is, all right, let's print these things. Let's do some debugging. Debuggery. Some debuggery here. I did this wrong. It's not if best is less than S, if best is greater than S. That might be why. That'll do it. I think I got the lexicographically largest string. Okay, a little bit better. This one at least is correct. That's good. This one is not correct though. Still got 42. So I got 97, 92, 97, 29, 42, 74. Huh. Okay. I'll do before rotation, after rotation. Say before, and then after rotation. I also added yeah, I think this is okay. So 97. Then there's a single rotation, I think. So that's maybe a little bit confusing. Add all the values, then perform a single rotation. Okay. So after the rotation, 92 and 97. Okay, let's do it this way. Let's do before first rotation. This is a little bit complex. I'm pretty sure there's a bug somewhere in my code. There are definitely some bugs somewhere. So after first rotation, before first rotation, after first rotation. There are a few different operations here that are going on that I probably should track. before optimal rotation. And then after optimal rotation. That's kind of what I want to check. Okay. I'll take my leave. Keep up the hard work. Carpe diem. Okay, take care, Yash. I appreciate it coming by, saying hello. Thank you. Absolutely. Yeah, absolutely. Take care. Take care. It's foundational. I mean, the C, yes, C is really good for the foundational stuff. I don't know about AI, but that much, but I use it when I take classes of languages. By the way, you're so kind. I mean it. Yeah, thank you. Yeah, I try to be nice to folks. But yeah, you don't need to know much about AI. I was just saying you just type questions into the box and it'll give you answers. That's all I meant. I didn't mean like you don't need to learn more about AI than that at their starting point. But I was just suggesting that it's a very good tool. Okay, before first rotation 79, after the first rotation 97, before the optimal rotation it's 92, and then after. Okay, so this is wrong. So this should have given me 29. This should have rotated to 29. So the rotation didn't work properly. Okay. All right. What did I get for the rotate index? So something's not right. Yeah, that was one of the things I wanted to see, is whether or not the rotation was happening correctly, which it looks like it's not. Okay, this rotate index came back 0, which it's not, and this one came out 0 as well. Okay, so let's do a couple things. Let's dump the code that I wrote here into into the AI and see what it says. I definitely have a mistake somewhere here that I'm not aware of. Oh, I know it's wrong. I think I know it's wrong. Or no, I don't know it's wrong, but it's the this should be multiplied by the block size, the rotation point, firstly. Secondly, I think this gives me the block just before. I could be wrong about that. I think I'm supposed to add 1 to it. I could be wrong about this. It'll give me the correct answer here if I do that, but it won't give me the right answer in this case. No. I think this is not. It's supposed to be a +1. Oh. What? Wait a minute, what? Oh, excuse me. Hold on. It's this one. Oops. Oops. I might need to add 1 in both cases, actually. Yeah, could be that I need this. It could be it could just be an off by one error. I'm not sure though. I have to test more cases. Interesting. Pretty interesting. Let's see some more test cases. Let's add more characters. Let's make this like a 5. Make this like a 4. How large can B? I think B can be up to N. Yeah, can be pretty large. It's a very interesting question, by the way. This is an interesting question. Let's see if I got it. I don't think so. I think it's probably wrong. Ooh. Oh, that's not good. Not quite sure what happened there. Yeah, I think this should be also mod equals N. That also could be an issue. That might be a problem. I'm wondering if that's a problem. No, something else going on. Okay. Wonder why. Does it say which function? Could be the block comparison, maybe. I'm not sure. Let me see if I could print. Okay, so I get a runtime error. I'm not quite sure why. All right. I don't know. All right, let's try this. Okay. So it's something to do with the block size. Let's see. See if I can figure out why I'm getting a runtime error. The odd case seems to be okay. Let's do this. Do I get the same issue in the odd case? I wonder. Yeah. Okay. So it looks like it's fine if it's odd, but if it's even, I get a runtime error. I'm not quite sure why. Let's see the code again. Kind of have duplicated code here. So the odd case is this one. It's actually the more complex one. It's the even case that's causing issues, which is weird. That's the simpler case. Why, GCD block size is GCD of N and B. That's fine. Rotate index. Rotate. Okay. Yeah, I don't see why I would have any issues there. Huh. Let's just put debug. Gonna comment out the other debug strings. So it looks like, yeah, my rotation calculation just put me one index just before the rotation point for some reason. rather than exactly at the index of the rotation point, which is a little bit odd. Huh. I don't know. I just could I maybe try to see when does this cause an error. I get an overflow somewhere here. Stack buffer overflow. I0. First time. First call. K is less than N is fine. That shouldn't have any overflow. Maybe rotate index is causing the issue. I could try that. Test that. That might be it. Before call. Or just before call after. I suspect that's exactly the line of code that's having issues, but the other part should be fine. It's got to be the rotate block portion. Yeah. Okay. Okay. So this is having issues. All right. Okay. Why would that be the case? Oh, here it is. Oh, it tells you which line of code. Oh, whoops. Whoops. I totally forgot. Yeah, these need to wrap around. That's my mistake. I totally forgot about that. Completely forgot. Okay. That was goofy. That's my mistake. I just forgot about that wraparound code. It does actually tell you the offending line. That's good. I don't think I need this part, this mod 10, mod n part, by the way. It looks like my intuition was right, though, about the rotation point, that this is slightly, that the rotation index is slightly off. I think this might have to just be a plus block size or something here. It could be this part, I'm not sure. But there's some off by one error in there that it's not obvious. And that's why I have to update the rotation point slightly by adding one. I don't think I need this part. All right. Is there anything else here? Yeah, my implementation definitely is pretty involved. Oh shoot, is it buffering? Okay. Huh. Okay. Dang. So, pretty interesting. Looks like this is it. Looks like this is it. Yeah, my implementation was pretty involved. Do a little more testing. Oops, must be even. But this looks like it's. Oh, must be even. Oh, these are both. Oh, I see. Also, those of you who are just tuning in, we're curious which problem we're solving. We're looking at 1625 on LeetCode. It's kind of an involved question. The solution that I came up with is also pretty involved. Let me remove some of these earlier ones. Add some of these later ones. Add more rotations too. vary the rotation amount as well. And I don't know if this has 20 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, yeah. It's not 20. Let's add like 8 characters. 1, 2, 3, 4, oops. 4, 5, 6, 7, 8. Let's do something like this. Make sure my test cases are correct. Okay, it's wrong. All right, so I got something wrong. Not great. Not ideal. Don't know what I did wrong, but something's not right. Interesting. Huh. Okay. Let me see something here. Oh, that shouldn't have been an issue. Actually, block size should always be divisible. This value should always be divisible by the block size. Oh. That's actually an indication of something going wrong here. Yeah, I shouldn't actually have to do that. Huh. Interesting. Yeah, the block size necessarily divides n. So, this should never actually cause that issue. Oh, this has to be not less than n, but less than the, I see, okay. I see. This is going to be blocks, blocks. That's part of the issue here, okay. I don't actually need this n here. That might be part of the problem. Yeah. Okay. Let's try something like this. Okay, it's correct on the other cases, but it's not correct here. It's still wrong here for some reason. Compare blocks is fine. The number of blocks is fine. Okay. I think all of that is okay. It's just, Might be some kind of a logical error here that I don't realize. What happened here? I don't know. Attempts to solve. It's clever. Standard BFS DFS approach. Oh, I was supposed to use a BFS DFS. Oh no, I didn't realize. Oh no, critical bugs. Okay. Logically flawed. One extra block, missing the actual minimum rotation. Select the next one. Out of bound access. Safe by definition. Okay, hold on. Well, I guess I was supposed to do BFS DFS. Yeah, so apparently this is incorrect. Which I'm not sure about that one as well. Okay, let's try. Tries to optimize the addition operations using GCD-AB, A10, but the implementation is incorrect. Odd indices, the loop correctly adds amount. However, the outer loop repeatedly adds amount. Correctly simulates all reachable states for odd indices. Okay. Even indices would be as odd. Inner loop adds to even indices. This is wrong. You can add A to odd indices. Oh, maybe that's why. Okay, hold on. Well, that's confusing. Odd indices, you can only affect the even indices you rotate by an odd amount, making. This is when B is odd. Yeah, B is odd. The nested loop structure applies the addition cumulatively in a way that might skip states or apply them in the wrong order relative to rotations. Major logic error. Code modifies S in place cumulatively. State space exploration is messy. The standard approach iterates all 10 by 10 combinations of additions for every rotation. This code tries to be too clever by stepping it by GCD, but the interaction between rotation and cumulative addition is broken. I don't know if that's true. Rotation direction mismatch. B, the last B characters to the front. This is a left rotation. First B characters to the end. Unless the problem statement specifically asks for a left rotation, this is likely the opposite of the required operation. Oh, that might be why. Could be this mismatch, actually. Could be the issue. It's a left rotation. Okay. Yeah. That's probably the main problem. Okay. That's why. Because I tend to forget how this rotate works. So this is a left rotation. Okay. It should be a right rotation. So we could just do Could just do n minus b, I think. I think that's right. N minus b. I think this rotate index may have been correct, by the way, to begin with. Are these even or odd? Odd? Even. These are very close. These are totally different. Huh. These are so strange. Oh my gosh. Oh no. Oh, oh jeez. Hey, where and how do I learn to code, man? I want to learn Python. What's up? Sagnik Sengupta? Welcome, howdy. Where and how? So you can learn how to program like right online. I mean, here you go. Are you ready? Ready for this? Do a new conversation. Howdy. Where and how would a new programmer learn to program? How much time we got so far? It's about an hour and a half. Excuse me. Where to learn? New programmers can learn through self-paced online platforms, structured boot camps, or formal university degrees. Online learning platforms, flexible, often free entry points, free code camp, Code Academy, Data Camp, Coursera, EDX, coding boot camps, intensive short-term programs, General Assembly, Flatiron School, university degrees, how to learn effectively, active practice rather than passive consumption, start fundamentals, build projects immediately, engage with communities, Stack Overflow, consistency over intensity. How about LeetCode? How about using LeetCode? Learn with an AI assistant. That's a guide. Like I'm doing right now. Let's see. Highly effective but risky strategy. Accelerates learning if used as a tutor, hinders if used as a solver. Socratic tutor. There you go. So what is the Socratic tutor? The most effective approach treats the AI as an interview coach rather than a code generator, guided hints over solutions instead of asking for the answer, prompt the AI to provide incremental hints. For example, act as an interviewer, give me one hint at a time for this problem, do not reveal the full solution, forces you to perform the logical derivation, which is the core skill being tested, pattern recognition, excels at categorizing problems, solving or failing a problem, ask the AI to identify the underlying pattern, it's a sliding window or two-pointer problem. This helps build the mental framework needed to recognize similar problems in the future. Debugging and complexity analysis when your code fails, paste the error and your logic into the AI, ask it to explain why it failed or to analyze its time-space complexity of your approach compared to the optimal solution. Tools like Claude are particularly noted for clear step-by-step reasoning in this area. The illusion of competence, dangerous passive learning, yeah, loss of struggle. So you gotta struggle a bit. So it says attempt it alone, request a nudge, implement, review, explain. There you go. That's what I like to do, just as an aside. This is my approach. This is my approach. I like to use LeetCode and chat with the AI about it. Okay. So rotation direction mismatch, correct approach summary, possible rotation positions, trial 10, PSI trial 10, track the minimum directly to the best rotation using the Shylock algorithm, which is valid only after fixing the addition states. Because the addition states depend on the rotation, you cannot simply find the best rotation of the current string. You must check the minimal rotation for every combination of additions. Recommended effects: revert to the standard numeration for additions, but keep your best block rotation to quickly find the minimal rotation for a fixed addition state. Should I not bother with rotating in between for the odd values, given that the addition possibilities will always affect both the odd and even indexed values? Can probably just add directly to this. Do you think? I think this is right, actually. I can simplify my logic a little bit by doing, instead of rotating once, I can do, I don't need to do this rotation, I think. It's odd and then even, and then have the rotate index. I think that's a simpler logic. Hey man, really appreciate that love and support, dude. Yeah, absolutely. Should not bother rotating in between editions. Where is my okay, so still wrong. So these are totally wrong though. Like these are completely wrong. Okay. Something's not right here. I think, let's see, let's just see what it says. Oh, I set the amount to the GCD of A and 10. Oh, whoops. Oh, why did I do that? Whoops. That's not correct. Ah. Okay. Oh. That's supposed to be A. Oh, I was like, what am I doing wrong here? Doing something wrong here. Uh-huh. That's subtle. This is confusing. Got that one right though. What is going on? These are so wrong. Oh no. Okay. Huh. Interesting. Hmm. Let's see. Hi, bro. Give me live advice. What's up, Akash Barky? What kind of advice do you need, dude? What kind of advice do you need, man? I'm here, dude. I'm here. Modifies the string s cumulatively without ever resetting it to a base state. This causes the inner loops to add a to an already modified string, exploring states like s plus 2a, s plus 3, etc. A single pass, which breaks the logic of iterating through distinct addition states. Oh. It's supposed to separate rotation addition. Hmm. Um. This is confusing. Best advice you've ever received. You want me to give you my best advice? Oh man. I can't give that. I'll get in trouble on my YouTube channel if I give you the best advice. YouTube has some pretty high censorship bars, so I can't actually say explicitly what the best advice I ever got was. Oh, I can't say it. I get in trouble on YouTube. Get in too much trouble. I have to keep my technical YouTube channel a little more pristine. A little too naughty. It's a little too naughty. I can give you advice on a specific topic, maybe. If there's some topic you want to talk about, maybe say some words. Can cover all states, but it fails of how I combine the cumulative. I don't think this is the wrong part, by the way. I think this is not the issue. Code nests the loops incorrectly relative to the rotation and comparison steps. Outer loop. A to odd indices generates the odd states. Even indices on top of the already modified string. The missing states. Odd 2a, even 1a. I think this does give me the states odd equals ka, j, k, alpha. Nested cumulative loops generates the set of states. Mathematically, the set of reachable strings is correct. Covered. Critical logical flaw in higher code applies these states relative to the rotation. Check the state bleed problem. Modifies S in place and cumulatively. Oh, wait. Oh, wait. I think the problem is that I rotate S by the optimal rotation point, which is an issue because it may mix the even and odd states. Oh. Oh, that might be the problem. I didn't think about that. That's pretty subtle. Although this should always be correct on the even case. Yeah, it should always be correct on the even case if that's the problem. Which I think it's not. This has an issue in the even case. Yeah, I think there's just an off by one error on the even case. Also appears to be some kind of off by error. Causes me need to increment the rotation x by one block. The currently correct. Yeah, it's also weird. All right. So hello on personal growth. Personal growth. Okay. You gotta do hard things in order to grow. If you want to grow in life, you gotta do hard things. You gotta struggle. Gotta struggle in life. All right. We're gonna increment the rotate index. There's some off by one error here. And there's also an off by one error here. And then there's another issue where I need to rotate back, which I don't need to rotate back in the even case, but I do need to rotate back in this case. Which is interesting. So this is got to be, I think, n minus rotate index. So this is a left rotation of the rotate index portion, and I've got to perform a right in rotation of the same amount. I don't know if n is, I'll have to check if n is, yeah, n is defined here. Okay. Response. Did you get my response? Did you get what I was thinking about personal growth? Wrong answer. No. Oh, it's so close. It's so close. Oh, dang. Gosh. Well, golly. Well, golly. Huh. Wow. Okay. Well, shucks. Huh. Interesting. How this returns and how this interprets the iterator. Okay, return value. Zero-based block index. Example, if it returns 2, means the minimal rotation starts at the third block. Performs a left rotation. This is wrong. A is smaller, A is smaller, A is the winner. Should discard B, the larger one. Logic is inverted. No. Okay, got it. That's the issue. It's not an off by one error. The logic is wrong. Okay. Got it. So if I is the smaller one, you discard the other one. Okay, got it. Oh no. Actually a symptom of the algorithm discarding the correct candidate, keeping the suboptimal one. By fixing the inversion in switch cases, it will return the true minimal index. It will not need to increment. Okay. Still getting the wrong answer. Oh, so many things are right now. But this one's still wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, it's much better. But this is still an incorrect test case. Okay, a little bit better. Okay. Right, so there's still an error here somewhere, but I don't see it. Also, I think I'm starting to get the context window starting to get kind of large. Fix the comparison logic. However, the code still suffers from the 2 critical architectural flaws we identified. Parity mixing, still calling rotate inside the addition loops. Scrambles which digits. Oh, did I not? Is this an even or an odd case? This might be an even case. No, it's an odd case. Oh, I didn't rotate back. Oh. Oh, that's a mistake. Okay. I put this in the wrong spot. This doesn't need to be rotated, this does. Whoops. No, it's still wrong. Ah, what? What is this? What is this? Huh? Do I need to add 1 here? Maybe I do. Excuse me, remove the inner rotation entirely. It's actually unnecessary. If you iterate all unique rotations in the outer loop, the optimal rotation is simply one of the states you visit when you iterate R from 0 to n with step GCD bn. Here's the corrected structure. Huh. Code has 2 fatal flaws prevented from working regardless of the alpha 1 feeling. Rotating S inside the addition loops happens. Never check odd is 2a, even 0. The state where j is 0, no additions even is skipped for all I greater than 0 because the inner loop immediately adds a before checking. Decouple rotation and addition. I added some code to rotate backwards though. Should cover the desired states. Not sure what I'm missing exactly. Fixes the physical orientation of the string for the next iteration, but does not fix the parity mixing bug or the missing state bug. Wait, doesn't rotating it back same odd and even parity tamed? Huh. I'm very confused. Why is this wrong? Also, it's starting to get to the point where the rotating back does not preserve. Oh, it's giving me a headache. I'm trying to get help from the AI, and I think it's giving me wrong answers. No, this is incorrect. No, that's wrong. I rotate, I add, then rotate back. Again, the additions are still correct. Ah, my brain, man, my brain. Apologize for the confusion, okay. Even equals 0 state. Hmm. Are you sure? I think it's just that form adding first. However, that would give me A to A, etc. Amount times a times a to a. For the odd even pairs, since amount is something weird going on here. Bound bound is equal to 10 divided by GC. And 10 follows that bound times a odd 10 is equal to 0, 10. Oh. Yeah, so this GCD of a and 10 divides a. And so if you take bound times divided by this amount, 10 divided by this amount times a, the GCD divides a, which means this whole thing is going to be 0 mod 10. Yeah, it's a cyclic group coverage thing. Yeah, the logic is fine. Okay. For some reason, this code misses this case. I think my logic is correct. It just misses it misses this test case for some reason. S, A, and B. Uh, 7 and 15. Okay. I don't know. I don't know. Hmm. Oh, I feel like I need to take a nap. It's been a couple hours. It's good, probably time to take a break. All right. Cumulative logic covers the mathematical set of values, but for this specific case, your code fails to index out of bounds in the best block rotation helper when the string length is not perfectly divisible by the block size in the way the loop expects, or more likely, logic flaw in how the rotation index is applied relative to the cumulative state. The most probable cause of the specific failure is that best block rotation assumes the string is periodic block size. When you rotate inside the loop, you might create a state where the minimum rotation does not align with the block boundary of the current block size calculation. It's a simpler bug. Rotation, direction mismatch. Right rotation forms a left rotation. Just reading all this. It's going through a lot of stuff to check, but it's not getting the right issue. No, we already addressed this. Zero state. Could you walk through a particular test case? Tell me the result should be. I don't know why the code doesn't get the right test case. It doesn't get the right answer. That's really weird. It's really weird. That's just 7 is 15. Apparently I can get 3 zeros. 1, 1, 1 can go to 0. Or 2, 2, 2. Yeah. But it says there are 3 numbers, 3 zeros next to each other. Well, odds and evens, I mean, yeah, 3, 4, 3. You could do these go to 0. And the 4 goes to 0. That works. Should be able to do that. Should be able to add 7 to these ones. The even ones, or the even ones add a 7 once, and then the odd ones add a 7 several times until I get 0. Like 9 times. Excuse me. Add 7 once, you get 1. Add 7 again, you get 8. Add 7 again, you get 5. Add 7 again, you get 2. Add 7 again, you get 9. Add 7 again, you get 6. Add 7 again, you get 3. Add 7 again, you get 2. Add 7 times. 8 times, excuse me. Add 7 8 times. And you get 3 zeros across the board. But that doesn't give me the expected result. Ah. Okay, so I'm running out of context here. The context window is getting to having some issues. All right, we're gonna have another conversation here. So my code is wrong, but I don't quite know why. Let's see what happens. I should take a break, I think. Getting pretty tired here. Kind of just want to figure out what's wrong here, though. Yeah, I was getting sleepy. Oops. Mathematical optimization. Helper. Okay. Okay. Would you kindly execute this code step by step on these inputs? So there's something about these inputs that doesn't give me the right output, and I do think it's wrong, but I don't know, or my code is wrong, but I don't know what exactly is wrong. A is 17, B is 15. Or 7, rather. A is 7, B is 15. Let's see what it says. Let's see what it does. I should... So I can see by inspection that this 343 sevens could be added to each of those to get 3 zeros in a row, which should be able to be rotated to the front. So something's going on here that's not quite right. Excuse me. Yeah. This might be too much to ask. What about the odd equals A and even equals 7A cases? Specific. I think it's, I may have gotten the wrong one there. 0, 1, 2, 3, 4, 5, 6. That's even is 1 and odd is 7. Hmm. I need to go to sleep. I'm falling asleep over here. Okay. Okay, right. What does the string look like? Actually do to the string in that case. I think it's supposed to give me the right answer, but it appears to either skip that case or not consider it for some reason. I probably should do this by hand. I'm getting kind of like, sometimes the AI tools are just a little bit um they don't quite get you what you want. Excuse me. Would you kindly iterate? Would you kindly walk through this case step by step? It probably won't do that. I probably have to run basically run a debug routine here. I kind of have to. This is a little bit taxing. A little bit yeah, that's all right. Okay, a little boring, a little taxing. So okay. When I is 7, let's do it this way. Let's do debug. If I is 0 and j is 7. Let's do it like this. Let's do s and j. This maybe is a little bit easier too, so I can see exactly what comes out at 0 and 6. I'm still kind of tired though. Excuse me. Okay. So somewhere here I should see there should be 100 of these. Let's see if I get 100. Yeah, got 100 of these. But somewhere in here there should be 3 zeros across, which I don't see. So I think it's one application of J. So J should be 0. And that affects the even indices. which I think 4 is an even index. 0, 1, 2, 3, 4, 5, 6, 7. No, it's 7. 0, 1, 2, 3, 4, 5, 6, 7. So it's an odd index. So it should be no, the 3s are an even index, which is going to be this one. So J should be 0. J should be 0. And then the odd index should be like 7. So I should be like 7. J 0, I is 7. So what should we be looking for? I think actually I is more like 6. I think it's like 6, 0. Excuse me, it's really close. So 7, 0. Let's try 7, 0. There we go. Okay. This should give me the correct result. This should be rotated to the front, I think. Is that the right one? Yeah. Or it's very close. 0, 0, 0, 8, 8, 3. Yeah. And then 0, 4, 9, 7, I think. Yeah. 6, 9, 5, 0, 8, 8. Yeah. This is the right candidate, but this doesn't rotate properly. Why doesn't my rotation code? Yeah. So the cumulative part does reach this, but it doesn't. I'm getting really tired. It doesn't rotate this correctly. Let me actually do it this way. Hearing noises. I don't know. The hell is that noise? Excuse my language. Okay. So hearing things too. I think it's a bird or something. I don't know. Okay, true best rotation. The rotation helper function fails to find the optimal alignment for that specific configuration. Okay. We'll come back to that in a moment. Let me see. Okay. So looking for 7, 0, we said, right? Something weird's going on. It's all the test cases, but this one I misses. Okay. So rotate 0, 8, 8 instead of 0, 0, 0. Oh. 0, 8, 8 here. No, it should. Hmm. Yeah, the rotation logic is wrong. Okay. Okay. So there's part of the answer. But why is it wrong? Excuse me, the custom lambda is overly complex and prone to edge case errors with repeating patterns. Simple brute force check of all 16 rotations is faster to implement and guaranteed correct. Simple loop. No, but I don't want to use a simple. Specifically, algorithm likely a variation of Duval's algorithm, a custom block comparison to find the lexicographically smallest rotation efficiently. However, if the string has a specific pattern, the custom logic might terminate early. It might cause the search to stop before checking the true optimal rotation. The comparison block logic miss the true minimum. Repeating substrings or specific structures, which might advance past the actual starting index of the smallest rotation. No. Right. But I want to use the more optimal Duval's variant. Two-pointer block-based variant. Presumably, it's possible to do this. It may be that there's an issue with the block patterns. I'm not really sure. Also, this is taking a while to... Subtle bug in the pointer advancement logic when handling repeating patterns. Huh. But why is my specific implementation incorrect? It's mentioned block size is 1. In that case, the simple approach is basically what's being used here. Let me paste that code again. So the logic is wrong at the rotation point. The rotation logic is wrong. Block size is just 1. So this compare blocks is actually very straightforward in some sense. Oops. I wonder, the issue might be because it's, I might have to do some modular arithmetic somewhere in there. Might be the issue. I think that's the issue, actually. Really code that. I think that's the problem. I think this does need to be mod in or something. I don't know if that matters. It might matter. There's something subtle here that I don't fully understand. Oh, interesting. Uh, that is so confusing. No, this is still. Oh, what a headache. Oh boy. Not ideal. Not ideal. All right. Are you sure? Are you sure that standard two-pointer approach is actually correct? Now that we're discussing it, seems appears that maybe this isn't quite right. Oh, that's not good. Conflates two different algorithms, Duval's. Designed for Linden factorization, correctly handles periodicity by skipping the j minus k, the period length. Naive two-pointer. Simplified logic that assumes skipping k plus 1 is safe. This assumption is false for strings with internal periodicity. Skips valid starting positions within the repeating sequence. Okay. So comparing the rotation starting at the first 0 versus the second 0, matches for k equals 2. On mismatch, it executes j plus equals k plus 1, jump 3. The jump lands past the third 0, the true optimal start. You effectively pruned the correct answer because the algorithm assumed the period was k plus 1. Correct optimal approaches. Oh, mathematically unsound. Oh, it's a headache. All right, what about just plus K? Oh man. Oh, my soul. Soul. TLE. Oof. Right. Oh, but K is set to 0. Okay. Um. Oh, that's why. This is going to be plus K. That's why. Oh my gosh. Oh, my soul. My soul. Oh, that was kind of goofy. I just didn't. Yeah, I didn't catch that either. Yeah, I totally screwed that up. I just didn't see it. Okay. That was more of a typo than anything else. Oh gosh. Nope. It's not the periodist. It's not the periodist. Just forgot to use I plus K and J plus K. Not the comparisons. Blocks. Very easy fix. Oh man. Gosh. Whoops. Whoops. Oh my goodness, man. That's so goofy. Typo. I guess it was. Yeah, it was a refactoring typo. I don't know what to say about that. It's annoying that the AI missed that, but yeah, it's a refactoring typo that I just kind of forgot when I changed it to compare blocks instead of comparing character by character. It's very awkward. All right, let's try some other test cases. Let's remove a few of these. Let's grab a few of these ones. Add a few more characters. 9012, 9334. Let's change this to 3. Change this to 15. Let's do a little more stuff. Dang, man. Dang. Hi, what's up, Fruity Lip Balm? Howdy. Hope your day's going well. All right, I'm going to go for it. I'm going to go for it, man. This could be wrong. It's a good chance it's wrong. Oh, destroyed. Destroyed. I was going to say it's a good chance it's wrong. Because it's just such a peculiar thing that I'm trying to do here. Oh. Brutal. I was going to say it's probably wrong. There's a good chance it's wrong. Just because it's just there's too much code going on. It's like kind of unfamiliar code to me. It's like a lot of ways this could make mistakes here. So somehow this is wrong. All right. 006112 should have been 001524. All right, let's get the different results. Let's get that debug code again. Okay. So B is 5. Gulp. Oh no. Don't tell me this is wrong. No. 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 It's gonna be so hard to find what's wrong. All right, let's see. First things first, let's see if I even get the correct sequence here. So it should be, what did they say the answer was? 001524. Okay, 001524. So 00 means this 4 has to go to 0, or this 8 has to go to 0. Or something, two things need to go to 0. And then something else has to go to 4, or to go to 1. I'm not quite sure, but they said 00152. So somewhere in here is 00152. Okay. Okay. There it is. 152400. I'm hearing noises now. I keep thinking it's a bird, but I can't tell exactly what it is. So this didn't rotate all the way. It should have rotated 0152. Should have been 001524. Oh no. Zero 1524. Yeah, so it didn't skip the case. It got the right case, but it just didn't rotate this appropriately. Why doesn't this rotate properly? So in this case, what is your objective and why are you grinding LeetCode? Jeez. The objective is to get better at computer science, and that's why I'm grinding LeetCode. That's my objective. Sir. Getting better at programming, grinding LeetCode in order to do that. So what is why does this give me the right rotation? It's mathematically correct for the indices found. Why the algorithm failed? Found I is 1, so I is 4. Boundary condition. Terminates the search too early. Oh. Huh. Oh my gosh, I'm trying to read this output. This is a headache. Okay, oh my gosh. That's just like AI gibberish, man. Are you employed? Not as a software developer. No, at least not currently. No. I do have a job though, a part-time job. I'm looking to expand my income streams though, because my part-time job does not pay that well. Doesn't pay that well. Asking some probing questions here, man. But I don't know. I guess it's okay. I guess that's all right. I is 0, 1, 2, 3, 4. I is 4. Uh, huh. 1, 5, 2, 4, 0, 0. All right, so how does this work here? So this is I think it's birds I'm hearing. It's just birds making kind of a squeaky noise. It's a little distracting. Okay. 1, 5, 2, 0, 0. 1, 2, 1, 5, 2, 4, 0, 0 is 6. So n is 6. The amount, the GCD of A, what's A? A and B. A is 8 and B is 5. Okay. I don't really need to worry about A that much. I do need to worry about 5. Okay. All right. 1, 5, 2, 4, 0, 0, 6. The amount A and 10, I think that's just 2. Bound is 5. That's fine. Block size 5 and 6 is going to be a 1. Okay, yeah, I mean, all right. So the block size in this case is just 1. In which case, it rotates. It should rotate this to the front. But instead it just rotates this one. What do I get for the rotation index? Also want to know what values do I get for I and j. I'm not sure if these need to be less than or equal. I think it's less than. Okay. What's up, chat? What's up, chat? Let's go back down to this one here. So the rotation index is 5. 0, 1, 2, 3, 4, 5. It should be 4. Not 5. So 0, 1, that's what it starts at. Compares 1 and 5. 1 is smaller. So it jumps j forward. K is 0, so it just jumps 1 to 2, then to 3, then to 4, right? 4 is better than 1 or 0. It's 1. So then it jumps K doesn't change at all, so that jumps to 1, 2, 3, 4. So jumps 0, goes to 1, 2, 3, and then 4. Now, interestingly, they basically end up on top of each other, and one of them moves forward, so J is 5. Now I is 4 and J is 5. They compare their equal. We increment by 1 for K. And they should wrap around now. Okay. And that's part of the problem. And then I is 1, J is 4. Oh. Oh. Huh. What? The wraparound logic's not being handled correctly. Huh. I got 5 here. Should have gotten 4. Hmm. I think this is what I need. Yeah. I think that's always correct, by the way. I think that's just fine. These are subtle things, man. Super, super subtle. Oh my gosh. Oh, that's what you get for trusting AI code too much, man. Jeez. Jeez Louise. Should I go for it? I should probably just go for it. I'm gonna just go for it. There's a whole bunch of test cases I have to go through, which I don't really want it. Gosh. I probably should have, though. I should have. Dude, this is brutal. So annoying. This is so annoying. No. I'm not handling it correctly still. Oh my gosh, man. Okay. Yeah. Still not handling the wraparound correctly, I think. That's so irritating. I mean, I could just copy the string over twice and do it that way. That probably handles it fine, but I can almost guarantee that that's due to the excuse me, I can almost guarantee it's due to this code is not quite right. Nope. Okay. So what went wrong in the other part? This one. Let's go back to this case. I think it's this one. Oh man. Oh. Oh, interestingly, the other case is not right though. That's weird. That's really weird. Oh, okay. So I broke one case, but another case passes now. All right. Let's go back to this. Why is this not handled correctly? Let's think about it a little bit harder. This is really annoying, though, I have to say. This is so annoying. I have to think so hard. Where's my, somewhere around here. Let's go back. It's more towards the top off the edge, and it's not comparing correctly. And this probably should be mod n, I think. That's maybe the right understanding. Which I guess is okay. But I think I run into issues when I do. Let's just try that, see what happens. Okay. Mod n. It should be mod num blocks, actually. Let's go with this for now. See what I get. Oh, no. That's okay. My gosh, man. It's so bad on my part. Lots of thinking you gotta do, a lot of subtleties. Oh my gosh. It's great. That's all I had to do. Oh my goodness. Unbelievable. That's so funny. Okay. Jeez, man. Jeez, man. Alright, we're going for it again. Don't make me regret it. Don't make me regret it. Okay, look. Oh, we got it. Oh, we got it. Took so long. Oh, I had the basic idea, the correct idea, but the implementation was just all over the place. I got destroyed, dude. I got completely owned by this problem. Completely wrecked. Just wrecked. Wow. Yeah, I like this idea. I like this approach. This aligns with what I was thinking originally, but definitely this was pretty tough for me. This was hard for me to get right. I struggled with this for sure. I should be able to get 0 milliseconds. The whole purpose of this was to do this super fast, super efficiently. Hi, what's up, Shri? How's it going? Howdy, howdy. Howdy, howdy, howdy. Oh no! Don't tell me. Don't tell me all of that was to not get 100% runtime. Oh my gosh, you'll be so annoyed. You're kidding? No, come on, no. Oh, that's brutal. Oh, that's a rough one. Tell me I don't have any debug code in here. It needs to. I suspect. Well, yeah, it's just yeah. Let me. Oh my gosh, man. No, it's slow. Oh, there we go. We got it. Okay. It's not consistently 0 milliseconds, which is very disappointing. This should be like really fast. I think the reason might be because I have a double rotate here. Rotating this way and then rotating back. I think I should modify this rotation. Maybe, I don't know. I could actually modify the toggle here. Put a toggle. Do it this way. Boolean toggle equals false. Toggle, and then just say, instead of rotating this, I could just say toggle equals like, it's going to be like toggle XOR rotate index 1. So basically, bool, so const bool change parity is going to be rotate index and 1. And then if that happened, then toggle has to swap. The way this is going to work is we're going to add, these are going to be the even indices that we're adding values to. However, if I've just rotated and the rotation was an odd rotation, now those even value, that even subset is going to be where the odd subset's supposed to be. And so I've got to update the toggle. But I also need to do this like iteratively and correctly, because if I rotate back, then I have to change the toggle back as well. Yeah. I don't know if that's going to be correct. I'm going to try that. My instinct says an XOR on that is probably fine. No, that's not. So the cases are like toggle parity, change C parity, and then desired result. It's going to be 0, 0, 1, 1. Change parity 0, 1, 0, 1. All right. So if the toggle is 0 and we haven't changed parity, we should say 0, the new toggle. If the toggle is 0 and we've changed the parity, we should change the toggle to a 1. If the toggle is 1, but the parity hasn't changed, we stay with a 1. And then, yeah, it should be XOR. Toggle should be XOR with the changed parity. That's a new toggle. It's basically taking modulo 2 of how many times we added an odd rotation. No, this should be correct. This actually should be right. I don't know why suddenly it's wrong. Shucks. I think the toggle just toggles to not toggle each time. I'm even wrong about that too. I don't know. No. What is going on here? Part of the question is if there's even a rotation. Basically, if it's not 0, if rotate index is greater than 0, maybe that's the way to do it. Try to eliminate that second rotation part No. This is so annoying. This is so annoying. Okay. Just rotate by 1 then. I don't know why it's so complicated. That part's so hard. I don't want to do a second rotation, but I guess I have to. It's for some reason the logic isn't quite working the way I'd like it to. Okay, let me try again. Let's see. Now all these are wrong. Whoa. No, this is not the right logic. This is just straight up wrong. It's just wrong. And I don't know why. What is happening? What is going on? Oh, no, I see. It's gotta be block size. That's the issue. That's definitely part of the reason. No, that's also wrong. It's just wrong. I don't know. I don't know, man. What is going on? Why does it have to be this? What? Am I crazy? I clearly misunderstand something here. Let's try this again. No, this is what I had originally. And this was correct. But it's doing a lot of extra rotating it doesn't need to do. Which is dragging down the runtime. The average runtime is a lot lower than it should be. This is an efficient algorithm, broadly speaking, but it's definitely, this could be faster. Now, this doesn't make a lot of sense, though. What doesn't make sense is that I shouldn't have to rotate this extra part. I don't know why. My thinking was, well, I could just use this toggle. And then if the rotation is, the rotation's always going to be an odd rotation on something that's even. So it's always going to flip the parity after S has been rotated. And assuming it's not 0, because if it's 0, it didn't rotate at all. So as long as if rotate index is greater than 0, then that means that I've got to flip the parity. But for some reason, that doesn't work. For some reason, that's just not correct. I don't know why. Wasn't expecting that one. Yeah, it's wrong. He said wrong. He's wrong. I don't know why that's happening. I'm missing something important here. Oh, aha. That's it. Got it. That's subtle. These both need to be toggled. These both need to be toggled. Not toggle. Toggle. Oh. Okay, let's try that one. That might be it. That might be it. Oh. Look at that. Look at that. I like that. There we go. All right. All right. That's super subtle. That's super subtle, man. Jeez. Gosh. 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 Oh. No, it's wrong. Oh my gosh. Oh, it's so brutal. No. Uh, oh, that's funny. I see. Interesting. Oh my gosh. By the way, I think it's supposed to be up here, not here. That might be why. Oh my goodness. I make so many mistakes, don't I? So I made a big mistake. Ooh. I would guess that this is actually correct, but this apparently is wrong. I just need to ensure that these two sets are adding to the opposite. Like if this one's adding to the even set, this has to add to the odd set. But doesn't this do that? Apparently this doesn't do that, I don't know. Oh, that logic is definitely convoluted and complex and frustrating. Why would... how can I avoid that second rotation, man? I can't, can I? I don't think I can, man. Wondering if this is the problem. I don't think so. I don't know. I don't see it. My thinking is that this should be right, but it's wrong. I don't see why. I don't see it, man. Do you know about bro? What's up, Mr. Spidey Gaming? Do you know about GSOC? What is GSOC? Hey man, just got off LeetCode and you popped up. What's up, Sean? Hope your day's going well. Welcome, welcome. Yeah, man. Yeah, man. Doing some LeetCode over here. Doing some LeetCode over here. Although I'm getting destroyed by this problem. I got the answer finally, but and I got the optimal solution, but it's 1625. But I'm trying to optimize my solution very slightly, and I can't think through the logic properly. And I can't seem to think through the logic properly, man. It's killing me. It's killing me. For some reason, so these two I'm sure have to be different from each other in these two loops. This one and this one. One of them has to be the even set of numbers, the other one has to be the odd set of numbers. Or odd index numbers, even index numbers, odd index numbers. Excuse me. So this is right. They're different from there. And then the toggle is supposed to keep track of when I rotate. Oh, maybe the rotate index matters. Oh, because I could do two rotations. Oh, that's why. Oh. That's what's wrong. Oh, it's so subtle. I need a break. I'm so tired. I'm so tired of getting so many things wrong. And then I can just do. That's what it is. That's the issue. That's subtle. That was what I was trying to do something like that before. I had the right idea, but I incorrectly asserted it's not if the rotate index is non-zero, it's got to be an odd rotation index. And I also have to get the toggle correct across the loop. Oh man, that's so much faster. There we go. That's how we get rid of the other rotation. What I had in here before was I rotated and I just rotated it back. But I was like, well, wait a minute. Like, I should be able to handle this parity stuff by rotating it once because I'm modifying the set of odd index values and the set of even index values. So when I rotate it, those just basically swap parity. And so I should be able to just swap between those two, which is what I'm doing here. But what I did wrong was I forgot that if the rotation index does more than one block, that's an odd block, then it becomes an even rotation, not an odd rotation. So the even rotation doesn't change the parity. Yeah. Mistakes were made, man. Mistakes were made. Still kind of on the slower side, though. Like, there's still a lot of variance. Even with those changes, there's still considerable variance. I should probably explain how I solved this problem. Oh no, it's much better. It's much better. It's like a lot faster by not doing it should be like about twice as fast if I don't do the on average twice as fast if I don't do the extra rotation. I got absolutely destroyed by this question. Let me see if the AI can figure out whether this is correct or not. The AI is probably going to tell me it's wrong. It gets things wrong constantly. Dude, that's crazy. I should probably let me do a couple of things. I should probably explain the question, explain my solution, and then get off because I'm so tired. I need a break. I need to stop. It says it's still incorrect. This solution passes all test cases with 0 milliseconds on the test cases and 100% speed. Okay, no, it's a correct solution now. All right, let's explain the problem, explain my solution, and then I made so many mistakes trying to solve this, though. I got absolutely wrecked. Lexicographically smallest string after applying operations, given a string S of even length, consisting of digits from 0 to 9 and two integers A and B, can apply either of the following two operations any number of times in any order on S. Add A to all odd indices of S, 0 index digits post 9 are cycled back to 0. For example, if S is 3, 4, 5, 6 and A is 5, S becomes 3, 9, 5, 1. So this is the odd indexed values that I was describing. Rotate S to the right by B positions. For example, if S is 3, 4, 5, 6 and B is 1, S becomes 6, 3, 4, 5. So this is the rotation. Return the lexicographically smallest string you can obtain by applying the above operations any number of times on S. Return A. The string A is lexicographically smaller than a string, and then explains the lexicographically smaller. Okay, and they give some examples like 5525 with A is 9, B is 2, can get 2050 using these approaches. 7, 4, 5, and 1, we can rotate once and get, just update. Yeah, rotate once, get 4, 7, bump the 7 to a 2, and then rotate again, which is what they do. And so on. There's other examples. And it's a relatively small string, and it's even length string. Digits are going to be from 0 to 9. And the modifying digit is going to be 1 to 9, and then the rotation is going to be anything that's less than or equal to the size of the string. So very interesting overall. The solution I went with was let's see what the AI says, by the way. Specialized version of Duval's algorithm, or the two-pointer minimal rotation technique tailored for block-based rotations. Significantly reduces the search space. Two-pointer rotation is faster than standard library calls and brute force loops. State space pruning is optimal. Yeah, sweet. Awesome, but much better while being 100% is crazy. It's so funny. Which one's much better? Yeah. Much better. So the thing is, there are some key points here. Let's start with the Duvals and the specialized block variant. So it's a two-pointer version of Duval. So what it does is we're trying to find the lexicographically smallest suffix of the string. And the reason why the suffix specifically can be used is because of the Linden factorization. So Linden factorization implies that there is a suffix that is going to be the least lexicographically smallest sort of element of the string. If you rotate the string, rotate that to the front, then that string is lexicographically smallest of all possible rotations. That's the result of Linden factorization, which I'm not going to go over the whole thing at the moment because I went over it a few times already. So that's why we're looking for the lexicographically smallest suffix. This code is very special because it does it in a kind of a symmetric way where it tracks variables I, j, and k, where I and j are going to be the two suffixes it's going to compare, potential starting points, and k is the number of elements that have already been compared that are equal to each other. So it'll like compare from two different indices. It'll kind of go one by one, block by block in this case, a block variant, block by block, checking the blocks to see if they're all equal. Until they're not. When they're not, that's when these switch cases activate. So when they're equal to each other, you just keep incrementing k. When they're not equal to each other, you're going to reset k, and then the one that's losing is going to advance forward, and it's going to skip forward. It basically means that once there's a mismatch, all of the possible sort of in-betweens also mismatch, because if you think about it, like consider I and j, and then the mismatch, all of the possible comparisons up to that mismatch are also going to be mismatched if you were to kind of increment those values forward. And we said before that they're both equal to each other anyway. So scrubbing forward, you're going to get the same strings. So that means that the losing one, you can just skip forward and then keep comparing. So that's what's going on here. They both skip to the site of the mismatch +1. And then that's the two-pointer approach. It's pretty sophisticated, quite frankly. And then you return the minimum of those two, and you stop at there are like three different spots where you stop. You stop if I and j go off the edge, one of them goes off the edge, like you've basically processed the whole string. Also, you stop if the processing itself ends up taking up the whole string, which is not really possible most of the time, but technically can happen, I think. And then also, it's important to remember to, when you're comparing values of k, to wrap around, because the suffix that you're comparing actually, the suffix itself isn't going to wrap around, but the things you're comparing can wrap around, which matters because you'd want to take the basically, if you don't wrap around, you can get errors as you're comparing things that are towards the end. Things that are like a long string of the same character at the end could have issues. So that's Duval's. Then comparing blocks, so in some cases, if you want to do subsets of rotations instead of all the possible rotations for a string, you break it down into blocks of rotatable elements, and then the blocks, you compare them block by block, which is what's going on here. So this just returns three different values, 0, 1, or 2. 2 means the blocks are equal to each other. 0, 1 means 0 means the first block is smaller than the second block, and the 2 and 1 means the second block is larger than the, or excuse me, the first block is larger than the second block. And then there's some modification there with the block size to get the correct characters. So there's like sort of a level of abstraction that's happening there to make it a block variant of the substring search, suffix search, excuse me, the suffix search. And then there's another optimization here that splits between when the rotation, so that the not only are we doing like rotation searching to find the lexicographically smallest rotation, and also doing it on subsets, which is what's going on with B, but because it's an even string and B could be odd or even, if B is even and the string is also even, that means that because when we're adding elements, we're only adding them to the odd values, and I can never change over to add to the even values. It means that in that case, I can actually simplify my logic a little bit and just do the GCD of A, which is the digit that's being added, and 10, divide 10 by that GCD. That's the number of different strings that are even possible. Right? That's the number of times that I can actually add A to the odd values. And so that's how many strings to work with. So this ends up being like just a single loop with this adding to each character part, adding A to each character, and then rotating that lexicographically small string using that block rotation, and then comparing that to the best thing that we have. So it's very simple in the even case, and it's only 2, 5, or 10 iterations on the string, and the string is only 100 characters, so it's very, very fast. In the odd case, however, because I can do the odd indices, I can add A several times, and the even indices, I can also reach them and then add A several times. I've got to take the Cartesian product of those two possible states, of the odd and even getting a certain number of A values each. And so I have a double loop that does that. So the code just becomes slightly more complex. So the double loop, same idea though. The number of times A can be added is still only going to be 10 divided by the GCD of A and 10. And so that's what that bound is, just calculated here. And so I perform those two double loops. But I do something kind of clever where I use a toggle to make sure I'm tracking when things are shifted around after rotating, making sure I add the correct number of times A to the even set and the correct number of times A to the odd set. So that's what's going on with this toggle. Kind of sophisticated. And that it basically just tracks the parity changes, and it only has to update that toggle when the rotation index is odd, when the final rotation index is odd. And again, in each of these cases, so it's going to be 4, 25, or 100 possible variations on the original string S. So again, that's 100 characters, so it's going to be 400, 2,500, or 10,000, 2,500, or 10,000 operations more or less overall, which is very fast on modern computers, especially with optimized code. Which the compiler will optimize automatically. So this will be really efficient, and that's what's going on in the code. Hopefully that makes sense. Explain that in gory detail. Oh yeah, the rotation index, just by the way, this returns the block index, and you just multiply by the block size to get the actual character index, the character index in the original string. And the rotation is very straightforward. It'll left rotate that section to the front automatically. This takes linear time, so it's an efficient operation. It's actually the rotation takes a linear time. The best block rotation calculation takes linear time, and then the rotate also takes linear time. But what I was doing before was, instead of using this parity check, I was actually just rotating it back. Excuse me, which would give me like 3n kind of operations, and then not rotating back by using the changed parity, the toggle becomes 2n back to 2n. So arguably made it like 30% roughly, a third faster. The speed 30% faster, something like that. But yeah, that was actually slightly a mistake on my part when I said it was twice as fast. It's not twice as fast now. It's just much faster. It's more like something like 50% faster, I guess. I don't know. Anyway, so pretty long explanation. Also, we still what are we doing here? Oh, I think yes. Sorry, I'm checking something. Yeah, but still doesn't always get 100% for one reason or another. Still a significant server, variation. So even though it's better. So yeah, that's this question in gory detail, and what I did to solve it. I think we can move on now. Apparently I was supposed to solve this using a depth-first search, or BFS, basically like a greedy search algorithm, which is weird, quite frankly. I'm not sure even how I would do that. I think it's inefficient to do that, by the way. I guess I was supposed to just do every possible rotation and every possible combination. Yeah, I don't know about that one. That seems really inefficient overall. It seems like it would have been a lot less efficient if I did that. But apparently, I think that was what I was supposed to do, something like that. I don't know, some kind of DFS or BFS approach. I didn't see that the first time I saw this. I was like, I don't know, BFS, DFS. That didn't make sense to me. So anyway, let me get going. I need to take a break. I'm tired. But yeah, that was an interesting question. Pretty involved overall. And yeah, thank you all for watching. If you like the stream, don't forget to give it a like. And if you like the stuff I do, if you subscribe to the channel, you can see more of what I do. And I should go. I need to take a break. I would have to think more. I might have to come back to this question again to look at the DFS and the BFS and see how fast it is. I might need to do that because I didn't see the BFS DFS there. GG's, man. See you next time. Yeah, I appreciate you coming by, Sean. Thank you. Come by, say hello, and chat and watch. Yeah, I'm gonna get going. I'll get going. But yeah, I do actually probably have to come back to this later and get some more insight into the DFS BFS approach, because I didn't see it and I probably should have seen it. And this approach that I wrote would, even after doing it once, would still take a really long time to do it in an interview. Like, it's a little bit too much of a solution.